All right, students, let me try another video solution here. We ran out of time during the Zoom, had a busy day today, and a couple questions. So I thought I'd make video solutions here. Let's see. So number 50 from chapter 33 says this. It says, show that the RMS value of a sawtooth voltage shown in the figure is equal to the maximum divided by the square root of 3. Now, let me just emphasize, maybe for fuller understanding, is that RMS becomes a very powerful tool because if you wanted to calculate the average power, which you might say is current times voltage, or you might say is voltage squared divided by resistance, or you might say it is current squared R. All of those would work for the average power, but when the current is changing and the voltage is changing, which do you use? And do you use the maximum of these values? Do you use the average of these values? Do you use the RMS? And it's the RMS. That's why we have such a thing called the RMS value. So you want to take the RMS current and multiply it by the RMS voltage, or here you want to just take the RMS voltage and you square it, or here you want to take the RMS current and square it. But it's the RMS that leads to average power. So that's why we really care about RMS, because it does lead to the ultimate step. What we want is average power. But notice it's not average current that leads to average power. It's also not maximum current or maximum voltage that leads to average power. So again, if you just want to know kind of the average effect of your circuit and your average power, you would use then the RMS. So the RMS is, as the name stands for, or the initials stand for, RMS, is you take its value, you first square it, then you average it out, and then you take the root of it. So the voltage RMS would be to do this. If the voltage changes with time, you first square it. You then average it, so that means add it up, maybe over one cycle. So 0 to t, one cycle. And then you take the, average, sorry, you add it up and divide by that time. Okay. And then you take the square roots of all of this. And so, as the name implies, these are your operations. You square it first, then you average it, and then or mean of it, and then you take the root of it. Now, if we had something like, most of the time, a sinusoidal pattern, it turns out that a good way to represent the RMS is to say it is the peak value or the maximum value divided by the square root of 2. And that's the one that happens most often, are these sinusoidal patterns. However, not everything is sinusoidal. So this problem, number 50, is along those lines. And it is trying to, just kind of make you really understand what we mean by the RMS value. And so they give you something that is non-sinusoidal. It is what we call a sawtooth, because it starts at, it's a cycle, so you can define how you want to cycle it. But it would be at the minimum value and go straight up in a straight line to its maximum value and then repeat. So it drops back down and then repeats. So I'll just draw 2 cycles here. So if this is the voltage and this is time, that's 2 cycles. We only need to integrate over 1 cycle or get its average, because the same thing's going to happen over time. But if we call right here its maximum value, then it goes down to the negative of its maximum value. I suppose you might call it its minimum value. But this then would be the function that I need to put right there. Okay, so let's start off by saying, could you write down an equation for the voltage as a function of time? And hopefully, yeah, the period here is capital T, one cycle. That's how long it takes before it repeats. And this is just a line, so the equation for a line is this kind of this mx plus b, where the slope, or m is the slope. So let me start there. Let's see, the slope looks like over one whole cycle, it goes up by 2. So this is going to be 2 Vmax divided by 1 cycle. So there would be the slope, a rise of 2 Vmax going from here up to here, and a run of 1 cycle. The function is t. I know I kind of wrote this. This looks kind of funny. I said a function of time, and I wrote the equation of the traditional line with the x-axis, but that's really time there. That's our function. Okay, so there's our slope, there's our time, and now we have our intercept, which is minus v maximum. Okay, so now if we want to take this velocity as a function of time and square it, let's see, if you think of this as a, and I'll just put that together, minus b, you will get a squared. So this would be 2 squared v max squared period squared t squared. So there is the a squared. Then it would be minus 2 times a times b. That's another Vmax. So a squared. Let me just double check. The first term squared. Okay. Then minus, because there's a minus there, 2 times just a and b. And then plus b squared. All right. So now if we want to average it, we would go 1 over the period, and we would integrate for 1 period of this function. So let me write that as a 4 Vmax squared over period squared and t squared. That's the first term. Minus 4 Vmax again squared over a period times a single t, and then plus Vmax squared, and we're going to add that for 1 cycle. All right, so 1 over period goes here. So I will integrate by leaving the constants alone, okay? And then I have an integral of t squared. That makes t cubed over 3 with the limits of 0 to capital T. So it would become capital T cubed over 3 minus 0. Okay, and again leaving the constant alone. This would make t squared over 2, evaluated from 0 to capital T. And then this would be v max, so the integral of this would just be t, evaluated from 0 to t. All right, now if we simplify this a little bit, you can see the t's here. With the one outside, there is a cube with that one. With this, again, this t outside distributed, there's a t squared. And with that t outside, that t would cancel. And hopefully not a surprise then that the RMS value will be independent of the period. That's kind of what the idea of average power is. It doesn't depend on the cycle because it just keeps repeating itself. So there's some average. So not a surprise there. If we simplify this, then we are looking at 4 over 3. And this would be V max squared. Looks like here we would have a minus 2 V max squared. And then this would just be plus a V max. And it looks like I forgot to put a square there, but that should come on down there. Okay. So let's see here. This is 1 1/3, and this one makes 2 1/3. And so then when we subtract 2, we have 1/3 of V max squared. All right, so now the final step, now that I've squared it and I've integrated it, is now to take the square root. So V RMS is then the square root of V max squared over 3, which simplifies to the maximum divided by the square root of 3. So there is the proof that a sawtooth pattern, you would take its maximum divided by the square root of 3, whereas the sinusoidal one, the one we use most often, would be the maximum divided by the square root of 2. All right, hope that helped.